Hello, college Algebra 2 or Algebra 2 students out there. Mr. Record here from Avon High School. We're with my sixth period class, beginning our new unit 16, covering sequences and summation notation. So I've got a little interesting historical tidbit here for you guys to read. It says, in the 13th century, an Italian mathematician named Leonardo da Pisa. Yes, that's Pisa, not the pizza, but the building that leans, right? It's a city in Italy that's located north of Tuscany. And he was also known by a very famous name, Fibonacci. Maybe that's the name that some of you are familiar with. He investigated a rather interesting string of numbers. These numbers, if we separate them by commas, are going to be referred to as a sequence. And Fibonacci's special little sequence looked like this. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc. How many of you are familiar with the pattern in this particular problem? Because it's something that you may have investigated in another math class. And if you're not familiar with the pattern, it may not take a lot of effort for you guys to see, how do I get from a 2 after 1 and 1? How do I get to a 3 with 1 and 2, etc., etc.? So I want to try to see if I can get everybody to recognize the pattern. Anybody want to take a stab? The pattern is, Anthony, go ahead. The sum of the previous two numbers, exactly. For instance, if we go somewhere here in the middle, like 21, 21 just happens to be the sum of 8 and 13. Okay, big deal, right? So what? It's dumb. It's actually not dumb. Now, this guy was like 1200s, right? The 1200s, that's the 13th century. I mean, we're still sort of in the Dark Ages at that point, right? Dark Ages meaning most of the world is illiterate. There's sort of stagnation in terms of art, music. I mean, well, there's like hardly any music at that point. Architecture, you know, you could look at building structures in the year 600, and you could look at buildings in the 1300s. There's no difference. 500 years go by, and it's almost like we have nothing to show for it, right? Part of that's to blame, the plague was to blame for a lot of that, all right? But what happens with this particular Fibonacci series is the fact that if you were to take any two numbers and divide them, 55 divided by 34 or 89 divided by 55, these equal something very special. And it's something that's called the golden ratio. So many things in nature feature these numbers, from fruits to flowers. And as I said, the ratio of two consecutive Fibonacci numbers can be seen in art and architecture. So this golden ratio, does anybody know what the golden ratio is? Exactly. 1.618, if I can call it that. So that golden ratio, which is sometimes called the Greek letter phi, is typically what was used in architecture from that point on. In other words, if you look at the facade of a building, the width of the building would be 1.6 times as much as the height. Right? The Pantheon in Rome is like that. All of the not all, but many of the statues, if you go into like ancient Rome and even Greece and you look at some of these statues, they're larger than man size, but they're like 1.618 times. If you look at a cereal box on the shelf, or typically a box of snacks, crackers, or anything like that, very often they have this dimension, 1.6 times as tall as they are wide. Why? Because it's just appealing to the eye. Okay? Now, that may not be the case all the time, because economics drive that, and they want to make sure they manufacture a box that is the right size in order to optimize, the cost to make it and so forth, which is something that we're going to study in calculus. But this is a very interesting number. And as I said before, these numbers here are often seen in nature. Before pesticides and things like that came into existence, it was very, very rare for you to pick a flower out of a meadow and have it have any other petal arrangement outside of 3, 5, 8, 13, or 21. That's how many petals you would see on those flowers. We didn't really know how to explain it. Now, with hybridizations and pesticides, that has now changed. Okay? But if you take even something as so simple as like an orange, slice an orange in half, open it up, you know how oranges has those little chambers? That's typically going to have 8 chambers. Boom. Take an apple, slice it, open it up, it has 5 seed pods. Boom. We could go on and on and on. Talking about the spirals around a pineapple, the arrangements of the spires of a pine cone. All of them seem to gravitate towards these numbers, and it's really weird. It's really spooky. All right. Now, our focus isn't so much talking about those characteristics. If you really are interested in those characteristics, then you might want to think about taking discrete math here at Avon, because we have a whole chapter devoted to Fibonacci numbers. But I want to talk about the sequence idea of Fibonacci numbers. So if we look at the Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, all right, we think of them as being the output or the range of some kind of a function, where the domain is just simply the number at which the value occurs, the first number, the second number, the third number. All right? So we could conceivably use function notation. We could say this Fibonacci sequence with our first value is equal to 1, but yet the 5th value is equal to 5, or the 6th value is equal to 8. All right? But most often in this class, we are going to do this. We're going to think of them as isolated discrete numbers, discrete pieces of data, and therefore we're going to call a sub n the general term or the nth term, and the whole sequence is often going to have the set notation brackets, which these are called braces, by the way. In mathematics, you have parentheses, you have brackets, and you have braces as your different grouping symbols. All right. So here's our first definition. An infinite sequence is a function whose domain is the set of all positive integers. The function values or terms of the sequence are represented individually by a subscript 1, a subscript 2, on and on. Sequences whose domains consist only of the first n positive integers are called finite sequences. Right? In other words, if you have a sequence that's going to stop because it's only going to go up to, say, 12 terms, we say that it's finite. So for a first example, let's write the first 4 terms of the sequence whose nth term is given. So for this particular guy, you're just going to plug in 1, 2, 3, and 4 for n. So A1 would simply be 2 times 1 plus 5. You guys, it's very unlikely that you need to show this work. I just don't think that that's just something that you have to do. I think you're going to be able to do this in your head, and you're going to get 7. Finding a sub 2. 2 times 2 is 4, plus 5 is 9. A3 is 11. You guys can probably already pick out the pattern. A4, 7, 9, 11. What do you think it's going to be? 13. Okay? Generally speaking, full credit would be given for that particular presentation of the answer. Credit would also be given if you just wrote this. And I'm going to be honest, this is what most kids will write. Most kids will just say these 4 numbers separated by commas, and I would be okay with that. All right? Now, when you get to one like B, it might be a little bit more challenging because of this -1 to the n power. So we'll do the same thing. A sub 1, we're going to let n be 1. Now, what happens when you have -1 to the first? Well, you're going to get -1, right? But in the bottom, 2 to the first, which is 2 plus 1, is 3. So the first term is -1/3. Now, with a problem like B, I'd be a little bit more careful. I would take my time plugging these numbers in now. Now, if n were 2, what's negative 1 squared? Positive 1. And of course, downstairs, 2 squared is 4 plus 1 is 5. So now we're going to the term 1/5. How about the third term? Negative 1 cubed is going to take us back to a negative 1. And then what's 2 cubed plus 1? 9, right? And I'm sort of running out of room here, so click that. And then for a sub 4, negative 1 to the 4th is positive 1. 2 to the 4th plus 1 is 17, isn't it? So if you wanted to list the terms out, you get negative 1/3, positive 1/5, negative 1/9, positive 1/17. What is it that you can tell me about the signs? There's a word I'm looking for. The signs are, begins with an A. Alternating. That's a great word to use. We're going to use that word all the time in calculus, but not until calculus BC. That'll be senior year. All right? That alternating sign is to blame for this guy, wouldn't you think? All right. Note the difference between the graph of, say, a function 1 over x versus the sequence a sub n, which is 1 over n. So basically, I have on the left the graph of 1 over x, and on the right, I have the sequence 1 over n. Who can tell me what's different about them? Exactly. The function is continuous. In other words, all of the dots in between are connected because its domain consists of all real numbers. I could plug 1.3258 in for x if I wanted to. But over here, we don't have that. And the opposite of continuous in math is, would you believe? It's not non-continuous, although that's true. It's the word discrete. Discrete means you have isolated points. And the reason is because the domain is just the positive integers. 1, 2, 3. I don't know what's really going on in between these 2 points. Now that's funny. You can sort of speculate, and you can use the function sometimes for the sequence of points. We do that all the time in calculus. But for right now, we're just going to treat these as isolated points. Okay? Next, I want to talk to you about recursion formulas. To put it simply, a recursion formula just defines the nth term of a sequence as a function of its previous term. The Fibonacci sequence is very much like that. All right? So find the first 4 terms of the sequence in which you know the first term is 3, and the formula to find any of the subsequent terms is an is equal to 2 times a sub n minus 1 plus 5. Well, don't get so confused about what these n subscripts mean. A sub n minus 1 is a fancy way of saying the previous term, right? Because if you're looking for the nth term, it's the nth minus 1 that came before. So for this particular problem, we already know that a1 is 3. That's vitally important. So a2 would be 2 times the previous term, which would be a sub 2 minus 1, right? See how I plug this 2 in for that n? A sub 2 minus 1, which is a1, plus 5. Well, that's silly to write it like that. If I know that the 3 was my a1, we're just going to multiply 2 times 3 and add 5. A3 is going to be 2 times the previous term, which is 11 plus 5. And you can see that this thing is growing pretty quickly. Is that, what, 27? And what do you guys think A4 is? You guys getting 59? So you can kind of see that the beginning part of this is pretty easy. It's just arithmetic for the most part. All right, most of what I'm doing is just laying down some vocabulary and things like that. The homework will go pretty quickly, right? The practice that you guys are going to do. All right, I need to introduce this idea. Some of you may have seen this, some of you may have not. But if you ever see this, what does this mean? Does it mean 5? Sorry. You knew it was coming. You knew it was coming. Does it mean I'm happy about 5? I am so excited about the number 5. I can't contain it. 5. Like in math, we don't have this. We don't have 5. All right. So no. Now that we're all awake, it is just notation. And it is called factorial, and it's a very essential part of probability, you're going to find out. We use this a lot more in the next unit than we probably do in this unit. But basically, the definition is this. If n is a positive integer, and it must be, you can't take the factorial of something that's a decimal or something that's a negative. It just doesn't work. The notation in factorial is the product of all positive integers from n going all the way down to 1. So I suppose that this definition here works, but it probably doesn't kind of sit with you well because we don't have a specific n. Okay? I'll return to this here in a second. So if we look down here at the activity, it says find the values of the first 6 positive integers in factorial form. So 1 factorial is just 1 multiplied down to 1, which is what? 1. Yeah. 2 factorial, what do you think that is? It's 2 times 1, which is 2. Yeah, it's pretty easy. 1 factorial is 1, 2 factorial is 2. Oh, therefore 3 factorial is 6. Yeah, you're right. Good. I'm seeing if I could get you tricked. 3 times 2 times 1. Good. 4 factorial is 24. It's kind of nice if you guys could have these memorized down the road. We see them in calculus in both years. 5 factorial is 5, 4, 3, 2, 1, which is 120. And if you want to make this go fast, 6 factorial, think about it, guys. Isn't 6 factorial just 6 times 5 factorial? Think about it. True? It is, right? Take 6 times 120 and you get 720. All right? Now, go back to the box. How do you feel about this? 0 factorial is 1. Okay, so you take 0 factorial, that's 0 multiplied all the way down until you get to 1, which that already doesn't make sense, and you get 1. Anybody bothered by that? You should be bothered by that. I need you to accept this. Give me a week, and I'll tell you why it is that way, because it's really defined in a different way. It's defined in probability. How many ways can you take 0 books that you own and arrange them on a shelf? One way to do that. No books on the shelf. That's basically what it means. All right, and I know some of you have had a little bit of experience with probability from your teachers. We're just going to go into a little bit more depth next week with it. Okay, but that's why 0 factorial is 1. Now, let's take a look at some more advanced factorial problems here. So, for example 3, write the first 4 terms of the sequence whose nth term is given by this. So I'm just telling you that factorial could show up in some of your nth term expressions, so just be ready for it. So A1 would be, well, 20 divided by n plus 1, which would be 1 plus 1, which is 2 factorial. And if you want to simplify that, and I highly suggest you do if you want to get multiple choice questions correct, 20 over 2 factorial is 20 over 2, which is 10, right? So there's our first term. Okay, now for a sub 2, we're going to have 20 over 2 plus 1, which is 3 factorial, which is 20 over 6. And if we wanted to reduce that, we would get 10 thirds. Remember, all things on multiple choice will be reduced. Right? Free response, I really don't care what you guys do, as long as it's accurate. 20 over 3 plus 1, which is 4 factorial. So what is that? 20 over 24. And if you want to reduce that, 5/6, is that right? Divide top and bottom by 4. And then the fourth and final term is 20 over 5 factorial. 20 over 120, which reduces to 1/6. So this is a really crazy sequence, you guys. If I started here with 10, the next term would be 10 thirds, 5/6, and then 1/6. It would be really difficult for one to kind of guess what would the equation be that would make that series, which is kind of what we're ending with today. I won't ever be able to give you one like that. All right. Before we sort of close the door on factorials, let's do some more advanced simplification. Because if a student sees these, 14 factorial over 2 factorial times 12 factorial, yeah, it's going to be so easy to want to pick up your calculator, punch these things in, and see what you get. And every one of your calculators, even those scientific ones, has a factorial button. If you want to kind of experiment with it tonight or now really quickly, it's not really easily found. You're going to have to access your button that says PRB. You should have a button that says probability PRB. But if you hit that, I think you'll see an exclamation point. Okay? Now, if you're using, say, a graphing calculator, TI Inspire, whatever kind of thing, then you could type this in pretty much the way that it's written. 14 factorial over 2 factorial, 12 factorial. So I would say 14 with an exclamation point over 2 with an exclamation point times 12 with an exclamation point, and it'll spit out an answer. The answer is actually 91. But we want to make sure that we're able to handle this without the use of a calculator. Okay? And this one is probably borderline one of the trickier ones, but it can be done without too much crazy arithmetic. So how do we do that? Well, we look at this and we first of all say, hey, wait a minute. I see that this 12 factorial down in the bottom could cancel with a bunch of the stuff that's in this 14 factorial. Because, guys, I don't have 14 factorial memorized. I don't know what it is. I don't even know what 12 factorial is. They're huge. But we do know that 14 times 13 times 12 factorial would comprise that numerator, wouldn't it? So see how I want to stop there? Now the bottom, I could go ahead and call 2 factorial 2, because that's what he is. Keep the 12 with its factorial, and then what's about to happen? Of course, the 12 factorials cancel with each other. Now, you can take 14 and cancel it with the 2, which is going to give you a 7. And then all that's left is to multiply 13 times 7. Okay, hey, maybe we don't have our 13's times tables memorized. Is it the end of the world? Of course not. Off to the side, just multiply 13 times 7. Kind of feel like you're back in 4th grade all of a sudden. And you'll get your 91. And it's not going to take a lot of effort. Okay? So you want to be really prepared for that. The prognostication, the prognosis for your tests over this, your quiz over this, would be a strictly all no calculator, because I just don't see where there's going to be any need to use one. All right? Now, if you look at B, B is a little bit more in general. Anybody want to take a stab? What do you think n plus 1 factorial over n factorial would be? What do you think? You're close. 1 plus 1 over n. It's not quite that. It's much less complicated than that. Because you got to think about n plus 1 factorial as one thing. In other words, you can't distribute the factorial. So let's take n plus 1 and let's multiply it by all of the stuff that's less than n plus 1 by 1 unit, right? Because that's what a factorial is. So what is the term, the integer that's 1 less than n plus 1? N. So if I stop right there at n and put the factorial, isn't that the same as n plus 1 factorial? It's kind of like what we did in this part A, except I had to write 2 numbers first before I stopped. Isn't that kind of neat? Now the denominator is n factorial, and then what happens? These cancel. And so the answer is just n plus 1, no factorial at all. Okay, and I promise you, if we played around with numbers, I don't know, let's pick one. Let's let n be 5. 5 plus 1 factorial is 6. Let's do one that's easier. Let's let n be 3. 3 plus 1 factorial is 4 factorial over 3 factorial. Isn't the answer 4? So the answer is whatever you had in the numerator without the factorial. Okay? Using the same idea, what do you think C is? Any ideas, Rafi? Not quite. And I think I see what you did there. Not quite. Livy, I think you were next. You're closer. It's n times some. Oh no, wait a minute. Livy's right. I had the problem in my mind wrong. I think she said n, and that is the right answer. Here's the trick. What is the integer less than n? N minus 1. So basically, guys, you just take the one that's larger, which is the n, throw the factorial after this n minus 1, after you've broken it down, and then you see the cancellation. Boom, boom. Okay. These are good. You know, I'll tell you what, I have to remind my BC students how to do these when they come back up in Calc BC, so it's all right. And then lastly today, summation notation. I don't know how familiar you guys are with this because it's typically not in our Algebra 1 program. We don't really talk about it much in geometry. It's a pretty easy symbol. It's the Greek letter sigma, which is synonymous with our English letter S. A lot of people think, no, this looks like the letter E. No, there's a Greek letter that looks more like our letter E. It's called this, epsilon. Capital epsilon looks like that. So the summation is called S for a reason because S is the Romanized word for sum. So it says the sum of the first n terms of a sequence is represented by summation notation. So if you have A with this subscript of I, and I want to add this A over and over and over and over. So I can let I start with 1 and take it up really as high as I want it to go. I'm just going to get A sub 1, add, go to the next I, A sub 2, add, go to the next I, A sub 3, etc., etc. Those of you who are pretty good at coding, computer programming, you probably do this all the time. They're called loops, right? It's the same thing. This is the mathematical version of loop. In fact, when you program a loop into your programs, this is essentially what you're doing. Okay? A couple of pieces of vocab. I is the index of summation. N is the upper limit. And 1 here is the lower limit. Okay? The index doesn't always have to be the number I. I wonder why they use I for the index. oh, because index starts with I, it makes it easy. But sometimes I see J and K. You know, in math, you got to think contextually. Earlier in the year, didn't we learn something else that I represents? Like, oh my gosh, something crazy, square root of -1. That's not what I means here, right? So we just have to understand that in this context, I is something completely different. So for our example here, expand and evaluate the sum. So if they ask us the summation of 2i squared as I goes from 1 to 6, well, to expand this, we just simply systematically let I go from 1 to 6. So we'd have 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared plus 2 times 4 squared. Aren't you glad I didn't take this up to 60? 2 times 5 squared plus 2 times 6 squared. This would be about as worse as it would ever get, because that's silly to have to do that much busy work. But it does ask you to evaluate. So 2 times 1 is 2. 2 times 4 is 8. 2 times 9, right, is 18. Now it starts to get tricky. 2 times 16 is 32. 2 times 25 is 50. And then finally, 2 times 36 is 72. Okay? And if I was going to add this together, I would probably group them. You know, those two guys make 10. These two guys make 50. This guy is 50. This guy is 72. And then I can add them without a calculator pretty easy. 182, is that right? Okay. There is very, very likely a button on every one of your calculators. Please don't look for it now because it's a little tougher to find. You have to go into like 2 different menus, sum sequence, and you can do this on a scientific calculator. There's a button on your graphing calculators that actually has a summation. So, all right, take a look at B. B is going to be a lot quicker, guys, because I'm only going from my index from 3 to 5. So if K is 3, we've got 2 cubed minus 3 plus, now if K is 4, 2 to the 4th minus 3 plus, and if K is 5, 2 to the 5th minus 3. Does that all make sense? You do not have to put these terms in parentheses, although it's nice, I guess, if you do. It does sort of organize things nicely. But here you got to do all the busy work. So 2 cubed, which is what? 8. 8 minus 3 is 5. Anybody know what 2 to the 4th is? 16, yeah. Minus 3 is 13. 2 to the 5th is 32 minus 3 is 29. And if we add these together, 18 and 29 is 47. All right, part C. Summation of 4. What the heck? 4. Yeah, so I want you to replace the I that you see with this 4 with 1, 2, 3, 4, and 5 and add them, because that's what the summation means. The summation means add. So replace the I with 1. Got it. Let's use a different color here, though. Replace the I with 1. Got it. Okay, next term. Let the I be 2. Got it. You guys see what's happening here? It's kind of silly, but that's what's going on. If you had to expand this, it's 4 plus 4 plus 4 plus 4 plus 4, which of course is 4 times 5, or 20. So you can put a summation with a constant. It can be done. All right. And then the final piece. This is the part that can be a little bit more challenging for students, and we're going to just kind of open the door to this. We're not going to go into a lot of detail with it, but I'm going to see how good we are working backwards. In other words, I give you a series. 1 squared plus 2 squared plus 3 squared plus all the way up to 9 squared. I want you to write this in summation notation. So I'm going to give you a hint. Your answer has one of these in it. This is probably the first time some of you have ever written that symbol. All right? pick an index. What letter would you like to use for your index? I, okay. Now, does it seem logical where we're going to start this I? Maybe the number 1? And if that seems logical, where do you think we're going to end it? What's the largest thing that we kind of see at the end here? A 9. Okay. All right, now the question is, what is the formula? I is going to change from 1 to 2 to 3 to 4 all the way up to 9, but then what are we going to do with each of those numbers? Square them. Boom. And there it is. That's all you do. And that's an easy one. That's probably as easy as they'll ever get. We actually do this in Calc BC and AB, and we tackle some pretty rough ones, make you think a little bit. All right, let's do the same thing for this guy. Give you a hint, your answer is going to have a summation in it. You want to use I again? Okay. Now, maybe you guys aren't comfortable telling me what to start I with, and that's fine. And if you aren't, that's okay. But look at every one of the terms in the sequence, in the series. What do they all have in common? They're what kind of number? Even the first one, if you make it that. Aren't they fractions? I know if you're thinking, hey, the first one's not a fraction. What are you talking about? Yeah, let's call it 1 over 1. It's a fraction. So not only are all these terms fractions, they each have a numerator of 1. Okay. So I think you can definitely say that this is the summation of 1 over something. Now, what do the denominators look like? What kind of numbers are 1, 2, 4, 8, 16? Yeah. They're 2 to some power. And it's funny how some students overthink the power because they could just use that guy right there. But I want to show you that most of you probably wouldn't think to use that. Some of you might want to use n here. And if that's the case, you would start at 1 and finish with it's hard to see if it's infinity because this thing would have to go on ... So what I'm going to do is I'm going to change this n because that's not what I want there. I want the letter I. I need I to be the exponent because I is what's going to change. But my upper boundary, my upper limit is going to be an n. Now, another way to say this, you guys, if you want it to look like this problem, you could use I minus 1 as the exponent. And in this case, you would start your I at, you could start it at 1 still, couldn't you? And this would still be an n. It's kind of funny, but either one of these is correct. All right? Either one of these is going to work. Oh, wait a minute. Time out. This first one's not going to work. I got to make an adjustment. Sorry. What would my lower bound be? 0. All right. That takes care of us today. There's a few properties here that I think are pretty self-explanatory, but we will finish up next time. Thanks for joining us.